In this lecture on dry etching, we are going to look at tools that we use to do dry etching of various material. So, we will look at various configurations, what are all the advantages and disadvantages of using those configurations, and also evolution of these configurations over years. So, plasma systems have evolved over time, right. So, the barrel system was the first of its kind that came into the industry. We'll see that in the next slide. And then there is a chemical downstream etching. Right, it's not necessarily the parallel plate or the inductively coupled system that we saw earlier. This is a very different type of system where all the radicals are created and then it is fed downstream. And then the next type is capacitively coupled system. So this is one of the popular configuration. So you can either use RF diode, dual frequency, triode single frequency, triode dual frequency. All these configurations have been introduced to test, and some of these configurations are not used in industry, but nonetheless we would like to go through it to understand the nature of this configuration, so that you will have better idea about how we control the plasma. The next is the high density sources, where we use inductively coupled plasma, right. So this is very different from the capacitive coupled configuration, and electron cyclotron configuration as well, so which creates high density plasma. So in capacitively coupled system, the plasma density is limited, right. We will see the reasons why it is, and then justify the configuration change. So barrel reactor, this is a legacy system where you will see a barrel, right, that is surrounded by the electrode. So the electrodes are fed with RF, and you can see this is a field electrode, and then you have a ground electrode here, and you have gas that is going in, right. And then you can suck out the gas on the other side through the vacuum, and in the presence of gas and your field, you generate plasma, right. So the interesting thing is, if you take the barrel, right, so the electrodes are placed in such a way that you create a uniform plasma. So here you have the ground, right, and then you have the RF feed on both the sides, right. So in this case, you create plasma in a uniform manner, right. So this is a isotropic plasma. So because of the isotropic nature, this was primarily used for cleaning, right, and also photoresist removal. After doing all the etching, or if you want to remove the photoresist of any polymer sitting on the wafer, this is the best way to do that, because it attacks all the sides, right. And this is again a very interesting system called downstream plasma, because the wafer is sitting in a different chamber and the plasma is created in a different chamber. So here the plasma is created either using RF or microwave, and then it is pushed through this duct and all the radicals that are generated, because we are not interested in the electrons or whatever, right. So we are only interested in the radicals that are reactive in nature, and those free radicals are pushed through the system, and then here we can take those, extract those, and then make it react with the substrate, right. And this substrate holder can also be heated if you want, and then it is pumped out through this end. This is how you drive the differential in pressure, and then you can downstream the plasma. Okay, so let's look at more conventional glow discharges, primarily RF discharge. This is something we also saw earlier briefly. It can be either capacitive type or inductive type. Capacitive type is nothing but two plates, right, and these two plates could be either the source electrode and the chamber, right, which is grounded, or you have the source electrode with a dielectric and then the other thing is grounded, right. there are obvious reasons why you need a dielectric here, right? We'll see that in a minute, right? And the next thing is about inductive couple, right? In inductive coupling, you're going to use a current source, right? So you make a coil, and when you pass current through this coil, you will generate a magnetic field, and that magnetic field is going to create a current inside the chamber, and that is going to create the plasma. So let's look at different type of capacitively coupled system, right? So one is the planar diode geometry, right, which is very popular. So here we have an electrode and then gas inlet and outlet, of course, and then the chamber is grounded, right? So now the power is given to this electrode, and you might also have put the wafer here, right? And the one of the issues here is you won't be able to control the flux and the energy, right? What is flux is the amount of ions that you get, right? And the energy is nothing but the energy at which the ions come onto the substrate, right? Because you have both your wafer and your electrode on the same platform. Whatever energy you supply to the system also affects your wafer as well, right? So this will end up really sputtering the electrode. So then people came up with a single frequency planar triode system, right? So in this case you have two RF, right? So we had this problem of controlling the energy, right? So in this case people used two electrodes which has RF, but the interesting thing is both the frequencies are same, okay, and the third electrode is the ground electrode from the chamber, right? So this was introduced so that you can give feed from both the side, and in this case you have to alternate, right? The frequency from the top electrode and bottom electrode, so that you could transfer the energy to the system, at the same time protect the wafer from getting sputtered, right? So if you remember, when you energize the electrode, right, so you will have electrons getting accelerated out, but you will have ions that are coming in, right? So the energy, the high energy ions are going to hit this plate, okay? When they hit the plate with very large energy, you will have sputtering, right? You actually want only etching, chemical etching, let's say, but in this case you are going to have physical etching, and physical etching mean there is no selectivity. So this is going to actually remove all the material from this. So this was actually adapted to make this whole configuration as a deposition system, because the ion energy is large enough. So when you put a target here for deposition, you should be able to make deposition out of this system, because you can do sputtering, right? But in etching you don't want this, because you want selectivity and control and so on. So this this configuration did not find its way into the mainstream etching system adapted for sputtering, right? And then instead of using the same frequency, then people thought, why don't we adapt two frequency system, right? This is a dual frequency triode system, right? So here the ion bombardment that we saw for the top electrode, right? This is avoided by using a higher frequency, right, and lower power or so that you can reduce the ion that is bombarding the surface, and this is how you could protect the surface from sputtering, right? And the lower electrode is kept at lower frequency, and this is where you kept the wafer and so on, and then you can use your gases that are fed through the system to generate the plasma with this dual frequency configuration and do the etching. So what we avoided from using dual frequency is etching of one of the electrodes, and it's sputtering of one of the electrodes itself. So this is how this was handled. But then instead of using two frequencies, then people said, why don't we use two frequencies but then one electrode, right? But we can switch between these two, right? So that was the idea here. So you can switch between these two frequencies, so high frequency and low frequency, so that we can feed efficiently electrons into the system, right? Energize the plasma, at the same time reduce your ion bombardment, right? In one cycle you will feed the energy, in the next cycle you reduce the ion energies and you only take the radicals into the system for etching, right? So it's a combination of RF feed which was also popular, that can avoid all these sputtering issues as well, right? And now we have single electrode with two frequencies. And this is a cross section of how the configuration or the tool configuration will be. This is actually how it will look if you go and open a reactive ion etching chamber. There is the gas feed, and this is the shower head. Okay, so this is the shower head that you see, that puts all the gases through the system, right? And then this is the bottom plate, where you feed your power, right? And this is the body, this is the chamber body I was talking about, which is also grounded, and the plasma is created between the plate, the top plate that you see here, and the bottom plate, right, or the power plate, and the wafer will be kept here, right? This is how the configuration is done. The gases enter to this and then they will exit through this. Okay. And the next configuration is inductively coupled system. So when you say inductively coupled system, instead of a capacitor, right, the two parallel plates, you want to have a coil, right? So here what we see here is the cross section of such a coil, right? So you have one electrode here and then you create a coil. So now the field is going to be something like this, right? And this is a planar inductively coupled plasma system, right, where the coil is planar, right? So this is one of the configurations through which you can create the plasma, and this is a helical or cylindrical system, right? So instead of a planar geometry, you have the chamber dome here, and the chamber dome is surrounded by this current coil, right? So when you pass current through it, you will generate the plasma inside this dome, and you can also vary the amount of current you are going to feed and how much you want to generate and so on by using this tunable feed as well. Okay, so there is a possibility to tune not just the current going through, but also how many coils you are going to use and so on. And there is an important process relation we should understand, right? The one we constantly talk about, ion energy and ion flux, right? We need to control both ion energy and ion flux. So let us see why we need to do that. So let's take ICP as an example, right? So there is a dome, and this dome creates the plasma, and then my wafer is kept below this dome, and then here either you put it through an RF, right? So you have an RF and then going through, of course, through a blocking capacitor, and here you will also have an RF current feed. So when you generate it, plasma is generated here, right? You create plasma here, right? The plasma is generated here. But then all the radicals, right? So you have ions that are sitting here, right? Radicals are sitting here. But what we want is all these radicals should come and react with your wafer surface. Then only you can create chemical reaction, right? And how do we do that? How do we attract it? By applying the RF that we have here, right? So this RF should generate that attractive force for these radicals to come in and the ions to come in as well, right? So radicals are neutrals, right? So you cannot affect them through applying a field, but the ions can be brought in by using electric field, right? Let's look at how this ion flux and ion energy is affected, right? So when the ion energy is very large, right? So when you have very high ion energy coming onto the surface, then you will have wafer heating because it has high energy, right? So when the ion energy is very low, you will have negligible etching. Okay, so that is something we should be very careful about, because you can reduce your ion energy to reduce heat and the impact, but you should not reduce your etching itself, right? So the ion flux is also important. So large ion flux and large ion energy will result in heating. Okay, and when you have low ion flux, right, and then large ion energy, that's called low density plasma, right? The flux is low but the energy is high. But then your energy is moderate or low, but you have very high ion flux, that is called high density plasma. So high density plasma and low density plasma depends on the ion flux and ion energy. Okay, if you have both of them high, then you will have heating on the substrate. Okay, when both of them are very low, you will not have any etch at all. So one need to find a sweet spot between ion energy and ion flux. Let's see how this can be controlled, right? So there are two things, right? So let's again go through this doom configuration, right? And then here I have some bias. All right, so now there is a bias power, right? So bias power is what we supply to the wafer, right? That VDC is your bias. And then ion energy. What is the effect of bias power on ion energy and ion flux? So now let us look at what happens to ion flux and ion energy when you change the bias power. So now I am changing the bias power, right, in this axis, right? And what happens to the ion energy? So the ion energy, right, at constant source power. So the source power is nothing but whatever we give to this coil, right? This is the source power. The reason why we call it as source, because this is what creates the plasma. So we are not changing anything to the plasma, we are only changing the bias. So what will happen to the ion flux and ion energy? So ion energy will increase with respect to bias, right? That is because you are increasing, you are accelerating, right? So you are trying to push all the ions from the plasma onto the substrate. So naturally your ion energy will actually increase. Okay, but then ion flux, right? So ion flux will not see any difference, because the ion flux depends on your source, right? You cannot create more number of ions by changing your bias power, right? Your bias power will only affect your energy of the ions that is coming in. The flux depends on the available ions in the plasma, and that is controlled by source power. So since we kept the source power constant, your ion flux will remain constant. Okay, so that is something that we should understand. And the next thing is about source power, right? So this should be source power. So the source power on ion energy and ion flux. So in this case, what we are going to do is we are going to change the source power, and we are going to keep, let's say, the bias constant, right? So this is our bias. So this is going to be our self bias that we achieve. And now we are going to change the source power. That means I'm going to change the plasma itself, right? So when I increase the source power, right, what will happen? The ion flux will increase because I have more collision now. I am increasing the density of the plasma, right? And that is how you increase the plasma density, and that is going to affect our ion flux. So the ion flux will be affected. Okay, but let's look at ion energy. What will happen to ion energy? So we are keeping bias constant, you see. So the bias constant will not, which should not affect the ion energy, right? So the bias power is the one that is controlling the ion energy. So now increasing the ion flux, right? So I have increased the ion flux, but keeping the bias constant is reducing my ion energy, right? Why is that? The reason for reduction in ion energy is to do with the potential difference between your plasma and VDC, right? Your wafer and your plasma. So your energy depends on the potential difference between the plasma and your wafer. Okay, so initially the plasma was at slightly lower potential, let's say, okay, but now I am energizing it, right, by increasing the source power. So now my source power has increased and my plasma potential also has increased. So this increase in my plasma potential has reduced my potential drop between my bias voltage and the voltage drop in my plasma. Okay, so this reduction in the potential drop will reduce my ion energy. Okay, so this is very important to understand. This is how you will control in your etch process whether you want high ion energy or high ion flux. So which parameter should you change, right? So by understanding this, we can only change either bias power or source power, right, depending on what you want to change. And based on that ion energy flux, right, you can actually come up with various process regions, right. So high energy ions are required to create anisotropic etching, right. High energy ions are really necessary to create anisotropic etching. The degree of anisotropy depends on ion energy flow and flux as well, right. So both flux and the energy. So in this case the neutral flux is the important one. You have ion energy and neutral flux are important in creating this anisotropic edge. So let's look at what are all the implications of this. So the flux of your etching species, if it is very high with very low ion energy, you will have isotropic edge, right. Low neutral species, and then you have low ion coming in, you will have isotropic edge. But you want to have high energy ions, right, with reasonable flux of etchant, you will have isotropic, right. And if you want to increase the etch rate, you should move in this direction, right. And then based on the configuration of ion energy and flux, there are different, you can put all these different tools, and the configuration we saw can be placed accordingly. Okay, this is just for understanding which tool to use, right, if you want isotropic etch, and which tool to use if you want anisotropic etch, and so on. And this is again an inductively coupled plasma system which uses a combination of the planar and the doom system. So this creates the plasma inside here, right, by using the RF, that's a source RF, and then we have the bias RF fed through the capacitor, and where the wafer is kept on, right. and this is normally an electrostatic chuck, right? It pulls the wafer inside, and the chamber body is also grounded, right? So the chamber body also acts as the another electrode here, right? So this is if you look at the parallel plate configuration, this might look like a triode like system, right? The only thing is the source here is inductively coupled, unlike the other configuration where it is capacitively coupled. And the other configuration is electron cyclotron plasma. So here we use microwave and magnetic coils, right? So it's again a doom type system which has magnets to create that magnetic field, but then you need to have a current to energize it, right? So the microwave creates the required energy here in order to create the plasma, and the rest of the things is pulled through the pressure difference, right? And the DC bias that we apply. Unlike the other configuration that we saw ICP, here we use a DC instead of a RF feed, right? And this is also used in some of the R&D developments and also some industrial processes as well. And this is broadly the difference between the capacitive coupled system and inductively coupled system, right? So there is a large capacitance that you create between the electrode and the plasma, but in inductive coupling happens, between the coil and the plasma. So this requires very large voltage, the capacitive coupling, right? But in inductive coupling, you need large current, right? So there is a voltage source and there is a current source. So you can create high energy ions, right, that can bombard onto the surface, but then the power is distributed between electrons and positive ions. This is a very important drawback in a capacitive system, right? So the energy is now distributed between both electrons and positive ions. So what you want to do is efficiently transfer all the energy only to electrons, not to positive ions. So the reactive ion etching and RF sputtering are examples of a capacitive coupled system. On the other hand, in inductively coupled system, you use a time varying current, right? So there's an alternating current source that you apply that will create an electric field, right? And this is what makes it much more efficient, where most of the energy is only transferred to electrons, right? So we are not exposing to very high energy ions here. The reason for that is in this doom, whatever you have, all the ions are restricted to this region, because in the wafer is kept far away. But then in a parallel plate reactor, when you apply a source, the RF source here, and then you have your wafer here, so what happens is, when you increase the voltage drop across this, you will have energetic ions coming and hitting your wafer as well. So you are not exposing your wafer to high energy ions in this case. So power, as I mentioned earlier, is entirely supplied to electron, which allows you to generate high density plasma. Without supplying high energy to electrons, it is impossible to generate very efficient plasma with very high density, at the same time not affect your wafer. And that brings us to the end of this lecture on the tools, and we have seen how the ion energy and ion flux control is very important in etching. So in the next lecture we will see the importance of ions, the presence of ions and neutral radical in the etch process itself, when we look at the mechanism of etching.